talk and I'm sure you'll find something to discuss. Okay.
Well, thank you very much, Adrian, for this wonderful introduction and some unexpected faces. Just walked in. Hey, I thought you were gone. Especially came back for me. I appreciate it. This is an honor. Thank you very much. So, and thank you all for coming, and thanks a lot to the visitor committee for the invitation. So earlier today, Ethan was telling me that every day he gets a paper saying that what's wrong with Einstein's theory of gravity. So actually, I'm not going to say where actually Einstein gravity fails, but I'm going to make a prediction for where it's going to fail. So I'm not quite as confident as those other people, but I want to make a prediction, and that's what we're in business for, to make predictions in science. So there is one thing that's there are actually two facts that we kind of grow up with when we learn science. One of them, especially astrophysicists, one of them is that Einstein gravity is essentially one of the most successful theories in physics. It's, in a sense, it's the oldest theory, oldest surviving theory in physics. I guess quantum field theory goes back around the same time, but not quite as long. And it's been tested over and over, and in many cases with to several significant digits. So indeed, Einstein theory has been very successful. On the other hand, a lot of us, especially theoretical physicists, especially people at Perimeter Institute, make their living banking on the possible failure of Einstein's gravity. So everybody thinks that it ought to fail at some point, and then where does that happen? Is the big question. But there are very strong theoretical and to some extent observational arguments that Einstein's theory of gravity has to fail at some point. And then the big question is, where is that going to happen first? So then the most naive answer, or in some sense the most conservative answer, is you have to have accelerators that probe up to Planck energy. And that's the answer that you would hear in your undergraduate courses. But the question is, so the thing that I'm going to challenge during this talk, and I certainly encourage you to interrupt me at any point if you disagree, is that might happen much earlier. And then I'm going to highlight places that this failure is most likely to be seen first. So this is the outline of my talk. So I'm a cosmologist by training. So I'm going to talk about the problems of quantum gravity. So I guess historically what happens, I came from an astronomy department, as Adrian mentioned, Harvard Smithsonian Center for Astrophysics. Went to Perimeter, there everybody was working on quantum gravity, so I had to find a middle ground. So I'm going to tell you about the cosmologist's quantum gravity problem. So what type of problems does a cosmologist care about in quantum gravity? This is not necessarily the same problem that the string theorists or loop quantum gravity people care about. Then I'm going to talk about three different topics, which I want to propose to you might be the places we're going to first see failures of Einstein gravity. So I'm going to talk about light fields and the dynamics in the outer galaxy, in particular breakdown of equivalence principle in the outer galaxy. That's actually a topic that must be familiar with some of you guys, because there was a lot of work done here by Mark Kesden on that topic. And then I'm going to ask you a question, a provocative question, obviously. What if Newton knew quantum field theory? And I'm going to detail and elaborate on that question. And based on the answer, somewhat subjective answer to that question, I'm going to talk about implications for cosmology in the solar system, and also implications for neutron stars and their connection to the cosmological constant problem. So this is a summary and a very subjective summary of problems that the cosmologists would care about in quantum gravity. And in some sense, they are a rephrasing of the standard problem that you read in textbooks. But I'm trying to highlight the connection to the real world, to astrophysics and cosmology that people in this building, for example, care about. So there is a thing that string theorists and essentially people who work on fundamental physics care about, and that's the problem of infinitesimal quantum field theory, which is phrased as the normalizability of the fundamental theory, or finiteness. So ideally, you want a theory that's finite, but if you're not too idealistic, you might be content with a theory that's normalizable. And a standard model of particle physics satisfies that, but gravity does not. So this is the deep theoretical problem in quantum gravity. But it's not just a theoretical problem of quantum gravity. It's intimately connected to the problems in cosmology and astrophysics that we care about. In particular, it has to do with the initial conditions of the universe. Because that's essentially what happens. The breakdown of the divergences of quantum gravity, because gravity is not normalizable, may not be important for us today, but it affects things at early times. And Big Bang is exactly when this happens. So if you want to have a good understanding of the initial conditions of the universe, you have to address this problem. And people try to tiptoe around it, but I think if you want to be honest and confident about your answer, you have to address the problem of quantum gravity to address the problem of initial conditions. So that's what you may hear a lot about when you hear about quantum gravity, this problem of infinities and finiteness. But in fact, of much more immediate concern to cosmologists are these other sets of problems that I listed here, known as the cosmological constant problem. And this is a problem that most people who work on fundamental physics don't worry too much about, because it's just too hard and they don't have any solution for it. So they just try to avoid that. But on the other hand, I think these are the problems that are of much immediate concern for us, as opposed to this problem of normalizability that you have to really go to Planck energy to worry about. So one of the problems, the oldest problem is the cosmological constant problem, which has been with us for a long time. Most of you have heard about it in one form or another. But apparently it goes back to Pauli in the 1920s when he was developing the principles of quantum field theory. One of the calculations that he did was to calculate the density of vacuum, the ground state energy of photons that sit in a vacuum in a box. And he came up with a density that wasn't quite as big as what I have here, but it was big enough so that the moon couldn't fit in the universe, basically. The radius of the universe would have been smaller if that density was really there and gravitated. So the first problem was the fact that the moon wouldn't fit in the universe if actually the vacuum gravitated. Now we understand field theory better, and actually the number, if Pauli was here today and did the same calculation, he would have gotten something that was much, much bigger. So even humans wouldn't be able to exist in the universe like this, where vacuum gravitated at the rate that predicted or naturally from field theory. It's something like 10 to the 33 kilograms per cubic meter. So the new twist to the problem, and again you're all familiar with it, was that this vacuum energy was actually measured and was 60 orders of magnitude less than the predictions from a standard model of particle physics. Many call this the worst prediction of a standard model of particle physics, which sounds fair. And the curiosity about this, some people call this coincidence problem, but some people include it as part of this old and new cosmological constant problem, is the fact that these two, this number, the vacuum energy, sounds very close to the matter density on larger scales today, which sounds like a coincidence because vacuum energy is supposed to be a fundamental property of vacuum, but matter density is changing with time. So how come we happen to cast the universe right at the time that is comparable to the vacuum energy? So these are so the reason I listed these was that these are all problems that have to do with mergers or marriage of quantum mechanics and gravity. So they are really quantum gravity problems. And these are the things that need to be resolved in order for us to be confident about our astrophysics and about our cosmology. So let me get us started. And again, as I said, please don't hesitate to interrupt. So first, let me try to argue why we need to variable light fields in our universe. And the only light field that we know right now are photons and gravitons. Gravitons we don't really directly detect. The photons we do detect. But there are strong motivations from different theories of quantum gravity or UV complete theories that there must be other light fields out there. For example, in a string theory, so low energy string theory in 4 dimensions, if you compactify it down from 10 dimensions, it's expected that there should be many light fields in them, and there are different types of fields that exist. Whether they gain some mass, that's still large by cosmological scale. It's not clear, and people go back and forth. The fact that we don't obviously see these light fields living around us means that there must be some mechanism that gives these mass. But there are still people, and this is just an example, there are people arguing that there ought to be a spectrum of these light fields, and they must be protected. For some reason we don't see them right now, but these are natural predictions of the string theory. So it's not a slam dunk prediction. In some sense, you may argue there is no slam dunk prediction from a string theory. But anyway, this is something that's inspired by a string theory. So the other strong motivation for a light field is the observation of dark energy. Now, I told you that dark energy is, you have this coincidence problem that the actual value density of dark energy that you observe is much smaller than what you expect. And that sounds like a coincidence. One possibility, and it's not a very well cooked up possibility, but it sounds like a plausible scenario, is that dark energy is not really constant, it's a dynamical field. For some reason it looks constant to us right now, but it's something that actually evolves with time. And the easiest way to realize that is with a scalar field with mass less than 10 to the minus 33 electron volts. So that's another phenomenological motivation for a light field. A third possible motivation for a light field is our observations of neutrino masses that happen to be has the same scale as the scale of dark energy, so that's another amazing coincidence problem which actually I didn't mention before. So the scale of neutrino mass is 10 to the minus 3 electron volt is the same as scale of dark energy, or density of dark energy. And there are possibilities of coupling these two together, but they can only be done by introducing light scalar fields. Otherwise, there is no real way for these two to talk to each other. So that's another reason to think about light scalar fields. So if these scalar fields are out there, how come we don't see them? And this is one possible scenario, actually the strongest or most significant scenario that could shield scalar fields from being observed by laboratory experiments, for example. So this is known as chameleon mechanism, and was developed by Corey and Wilfman. So Justin Corey was a friend to the institute, so it's something that many of the people at PI are very familiar with, although Justin developed this when he was at Columbia. And the idea is that if you have a coupling between matter and these light fields, of course if you have no coupling you don't have to worry about it because it might be out there but you don't see it. But if there is some coupling, the question is why don't we see it, and what is it that fine-tunes this coupling to be as small as it is experimentally? And this mechanism explains how this would work. So if you imagine a coupling, and I'm simplifying things here, if you imagine a coupling between a scalar field phi and matter, and the most natural thing that you can imagine is basically conformal coupling geometric, gives you an effective potential for the field which is modulated by the density of matter. So in low density regions, this term is negligible, so you have a field, a potential that could be very flat. Of course, there is no need for it to be flat, but let's assume that that's what's happening. After all, it's a light field. So the minimum of the potential has this very small mass, but when you go to high density regions, this term becomes big, so you have this steep correction due to this density dependent term. And the minimum that you get is has much larger second derivative, so that means you have larger mass. So the implication of this is that you have a natural mechanism for making these light fields heavy in high density regions. And remember that all the constraints that we have on these fields are in high density regions, like solar system, on Earth, places where you have laboratories or you have precision experiments. So this would be a way to suppress the effect of this field in high density regions, because basically if you have a massive field, the forces would be short range, so the fifth force test would miss basically this field. But still it could be important on cosmological scales, because density is small on cosmological scales. So, so you have a long range force on cosmological scales. So what Corey and Weltman showed was the way this process works in practice is that every dense object forms a thin shell around it, and the field is only sourced by that thin shell. So things inside the dense object don't source the field. So anything outside this dense object don't see any stuff inside the thin shell. And the field is only sourced by this thin shell. That's why the effect of this fifth force is highly suppressed if it's caused by dense objects. Lower density objects, they wouldn't have a thin shell because force becomes long range, and everything, and you can see the full fifth force from the low density objects. But higher density objects are shielded because of this thin shell. So what we realized was actually, so one thing to have in mind is that this is not a nonlinear theory of gravity. The reason is that this d of phi is nonlinear. Obviously, you can see this potential is nonlinear. So the effect is going to be more subtle than just suppressing the force. A lot of the stuff that you expect from ordinary gravity is based on linearity, and that's not going to be true here. So in particular, for example, you don't have the principle of superposition. You cannot just add forces. Or the fact that an object doesn't exert a force on itself, that's not true anymore. There would be a self-force effect because it's a nonlinear theory. And a more straightforward way of seeing it is this simple geometry that I showed for you. And this is something that you find in Jackson or any other introductory electrostatics book. So I'm solving the cosine equation, or Laplace equation out here, where mass is small, and inside you have a very steep potential because mass is big, so the field would sit at its minimum, which is the constant. It just depends on the density. So what you're really have here is just conducting boundary condition in electrostatics. So if I put an object out here, and when I calculate the force that this guy exerts on this object, Jackson tells us that you have to change the field distribution. So the fact that you put an object here changes the field distribution everywhere. And the way we do it in a standard electrostatics is to put an image charge if it's a spherical object. So I'm going to have an attractive force due to the thin shell, but the fact that I put the object here changes the distribution of field inside, and in addition to this thin shell, I'm going to have this have to include the contribution of the image charge, which would be in the opposite direction of the original force. So basically, because image has the opposite, so it's opposite to electrostatics because masses are attractive, but in electrostatics, the same charges repel each other. So the image charge becomes repulsive here, as opposed to in electrostatics where image charge is attractive. And the size of the image charge depends on how big the object is. So the self-force is proportional to how big is your object. So this is what, so what we were working on, but I guess a group in, I guess in University of Washington beat us to it. But anyway, so the two papers that point out this analogy between electrostatics and chameleon. And this is Razi Proversan is a graduate student who actually proved this rigorously. So now what I'm going to do is that, so where are the places where this becomes important? We know on galactic scale, this drift force could be big. So maybe this could be a satellite galaxy, and this could be our Milky Way. So that's what we did. So we worked out the potential conditions in NFW profile, and sometimes the potential conditions work, sometimes they don't work. So the difference is that NFW profile is not a sharp density gradient in it, so it's basically gradual. So you don't always have the potential conditions. So it's very non-trivial to come up with the right conditions for it to satisfy. And in principle, in the real universe, depending on the parameters, it may or may not be satisfied. But if the potential is satisfied, the potential conditions are satisfied, then you can actually calculate this self-force, say, on the satellite galaxy. And this is an example that's close to the Milky Way parameters, but not exactly the same. So this is the circular velocity of a satellite galaxy as a function of its distance from the center. And basically, as you expect, there is a thin shell, at least for this choice of parameters. Inside the thin shell, the force is short range, so you don't have to worry about it. It doesn't do anything. When you go outside the thin shell, force becomes long range, and actually the velocity would become bigger than what you expect because there's extra force that increases gravitational force. That's why circular velocity is bigger. However, the self-force due to the image changes the result and depends on how big the satellite is. So you can see that for a small satellite galaxy, there is little effect, so you get little self-force. But for a big satellite galaxy, so these would be the biggest ones that we know, you can change the velocity by a order of 10%. And this is, so what basically this implies is a violation of equivalence principle in outer galaxies. Big galaxies see a different force than a smaller galaxy, which is something that others have predicted would happen in chameleon theories because it's not a linear theory of gravity, but this is an explicit way of calculating this effect. So the person who actually suggested testing this very precisely based on galactic observations was Mark Kesden with his PhD advisor Kamienowski, and he did these simulations of, in particular, Sagittarius galaxies, looking at how stars that are stripped from Sagittarius galaxy move in the galactic potential. But then if the stars see a different force than the galaxy, then they wouldn't be moving with the same velocities, even if they're at the same position, same radius for their orbits. So the tidal streams from the satellite galaxy would be very asymmetric because the stars would be moving faster or slower. And this is the simulation that he did. This beta parameter is what quantifies the difference between the two forces, or the two accelerations. So this cross here, which you cannot see very well, is where the Sagittarius galaxy is. And with beta equal to 0, the tidal streams are very symmetric. It's not very obvious, but basically you have the same number of stars on both sides. But as you're turning on these beta parameters, this is the most extreme case, beta equal to 0.3, all the stars are on one side of the galaxy. And that's basically the way you can constrain this beta parameter to about 10% accuracy. So our current prediction is somewhere close to that, but it's not. It's still less than what's currently constrained. And of course, this is only one satellite galaxy. You have, if the satellite galaxy happens to be sitting inside the thin shell, then you don't expect any effect. But you need to have this tidal stream right outside the thin shell to see the biggest effect, the biggest violation of equivalence. Yes?
What side of the galaxy is it? The side facing the side?
Sorry, I don't understand the question.
So in what direction is the asymmetry?
So that depends on the sign of beta. But basically the point is that if a stars see a bigger force, then they move faster. If they see a smaller force, they move slower. Yeah. So in this case, the stars would see a bigger force. So because they are like test objects, they would try to follow this. But then galaxies see their own image, so they would be moving slower than. Good.
This is a violation of GR because of the GR.
This is a violation of equivalence principle in the sense that different objects don't have the same acceleration.
Yeah, but W to the 5 is 1.5 times R.
That's right, exactly. But you have a potential as well, so it's not just that phi has a potential, and that's the reason.
You know, if you have a regular tide, a tidal distortion of a central body by the mass of the body moving around it, that is an effect of the extra acceleration because it distorts.
That's true.
And if something came off it, it made a smaller body because it was less massive. You would get a differential.
You're talking about in a standard GR or in this scenario?
I'm talking about Newtonian physics.
Yeah,
You
yeah.
have if you look at the orbit of a moon around here, as a tide,
Yeah.
that increases the monopole force on the moon by the climate force.
Yeah. No,
And then if a little piece came off the moon, it wouldn't make much of a tide on the Earth, and so they would be much smaller.
yeah.
And then remove different.
So, but I imagine this, yeah, so those effects are very small for a small object, right? And I guess the size.
effect is maybe a small effect. We have more separation.
Yeah, exactly. But the point is that this
similar. It gives a similar result.
you're right. But yeah, so the difference, of course, yeah, I mean, qualitatively they're the same, but quantitatively they're different. And the reason is that for very small objects, you still see this effect because the stars and galaxies see different force. Stars and satellite galaxies see a different force. But then in the tidal effects, they become small when the objects become small. But then I agree with you there. That's something to worry about if you want to do precision calculations, and that's something that Mike actually worried about. I understand he had some papers on how you can distinguish this effect from the standard effects that you have. Okay, so that's a good point. So this will be one of my bets as to where you're going to first see values of general relativity. And it relies on this idea that there should be direct fields, but that's something that's, as I said, I try to motivate based on different line varieties. So let's move on to the second problem. So we first talk about the issue of UV completion and how that should lead to large fields. From my own point of view, a much bigger problem with quantum gravity and our universe is a cosmological constant problem, as I discussed with you. So in particle physicist language, the left-hand side of Einstein equation is 10 to the minus 3 electron volt to the fourth on larger scales. But the right-hand side is 100 GeV to the fourth plus excitations. And for some reason, yeah, so this 100 GeV to the fourth is not, obviously you can see that there's a big discrepancy between the two sides. So the approach that most physicists have these days, and it's becoming more and more popular, we just had a conference at PI about different ways of thinking about it, is the so-called anthropic solution, anthropic principle. So maybe there are different copies of our universe, and we happen to live in a rare but habitable part of our cosmos. So the point is that most places with a big vacuum energy are not habitable, but since this is a random number, and some places it could be as small as we see it to be. So the problem is, so what I want to argue, and I don't want to dwell about it because people happen to be very religiously on one side or the other side of this argument. So I want to just tell you what's my point of view and then move on. I probably may not convince you. So this is a paper by the proponents of this scenario, the landscape or anthropic idea. So they say eternal inflation predicts that time will end. In particular, they say that the most successful measure proposals, our galaxy is likely to encounter the cutoff within the next 5 billion years. So that's their quote-unquote prediction. And I think these are, again, so these are the people who are proponents of the anthropic ideas. And I think the way I read this, and then we can go through the paper in more details, It's just that what this says, that whenever in any theory you're close to the cutoff of the theory, you don't trust it. So, sorry, and that means that I think even these people are considering that this theory is not predictive. Basically, that's basically what this means. So I think that's kind of the problem, that there is this big problem, and people have come up with one solution. But I think in accepting that solution, we are really making a choice. So there are two sets of principles in physics that we have adhered to during the 20th century. The one side, which probably goes back to Galileo, but Popper basically qualified them the way, stated them in the way that they are now known, the falsifiability of the theory and predictivity of the theory. On the other side, we have the principles of modern physics, which is Lorentz symmetry and locality, the stuff that Einstein taught us we should take seriously. Einstein told us there is no preferred frame and there is no action at a distance. And the principles of quantum mechanics, in particular an action principle, which is what you can only do quantum mechanics based on. So you can only do quantum mechanics for things that have action principle. And unitarity, which is another big principle of quantum mechanics. So what I feel is, and I cannot really prove it in any rigorous sense, is that we have come to a juncture that either, if you want to address the problems, the big problems of quantum gravity, and in particular the most important one being the cosmological constant problem, you are either giving up on falsifiability and predictivity of the problem, or the solution. If you don't want to give up on this, then you have to give up one of these principles. Because there have been smart people for the past 80 years trying to keep to these principles and come up with a solution, and they failed. The best they came up with is this. So that means that either you want to give up falsifiability and predictivity, or one of these principles must be wrong. So anyway, so there might be a smart person who comes up with something not next 10 years or maybe in the future, but it's the fact that people have thought about these problems for 80 years and hasn't quite worked says something. And what I want to suggest is maybe a different way would be to modify this equation. Instead of trying to find here in the right-hand side of it, say that this is not the right equation to use. And of course, we'll have to try to be consistent with all the other constraints that we have on Einstein gravity. As I started by saying, Einstein theory has been one of the most successful theories of nature, or you can argue the most successful theory of nature. So modifying, you can only modify it to your own peril if you're not careful. So, let me go back to this provocative question that I suggested. So I guess I'm halfway through, is that right? What if Newton knew quantum field theory? So you would think, okay, that cannot have to be right. But I mean, one can imagine that, special relativity was developed before general relativity. So you can imagine a scenario where we didn't really have any access to strong gravity or any test of gravity. So say, for example, if you couldn't see anything in the solar system, the Earth was covered with clouds. So we couldn't really test gravity very well. But special relativity was developed because you could do collider experiments and make very high energy particles. So we knew special relativity very well. And from that, you could get quantum mechanics very well, so you could get quantum field theory. But we had very poor understanding of gravity, or no understanding of gravity. So if Newton, at that time, tried to develop his theory of gravity, well, I would think maybe he wouldn't have written down this equation, or whatever exact, so I'm paraphrasing, so probably Newton didn't write things exactly in this form. But he knew this is what his equations meant. And the reason for that is that vacuum in quantum field theory has a huge energy. And if you just put it on the right-hand side of this equation, this would be blatantly inconsistency with any kind of experiment that we have. So maybe he would have written this equation. instead. And this is, remember, this is just Newtonian gravity. So what's the advantage of this equation? For everything that we can test gravity for, even today basically, almost everything, pressure is tiny compared to density. So actually this equation is almost the same as the equation that I wrote before. The only exception is for vacuum, this rho plus p over cs squared vanishes. So this equation has the property, at least at the Newtonian limit, that it's blind to vacuum energy. So whatever energy that there is in quantum field theory, this equation is insensitive to. But it's consistent with essentially every other test of gravity that we know, and I'm going to go through those in a little bit. But basically at the level of Newtonian gravity, you can see that pressure, because we know pressure is negligible compared to density for everything, say, in the solar system. This term doesn't really make a difference. So maybe that's what Newton would have done. Who knows? Of course, now we want to put everything in a covariant framework to be consistent with special relativity, or to fit the principle of relativity, I should say. General principle of general relativity. So we want a covariant equation that does the same thing for us. And it turns out that it's possible to do that. This would be a covariant version of the same equation that I wrote. And the only thing in it is, so this basically, the 0, 0 part of it is rho plus p. And what I'm doing here is I'm just basically subtracting the trace of energy momentum tensor. So if T mu nu has a vacuum part, the energy momentum tensor has a vacuum part. Plus excitation, these excitations will be particles. The vacuum part is subtracted on the right-hand side. So it does the same thing that this other equation would have done. There is a problem with these equations, and I would have asked you to guess the problem, but I already say what it is. So I'm going to spare you the trouble. And this is the only slide that's going to have equations really. So you don't have to care too much about this. So the point is that this doesn't satisfy, if I didn't have these three dots here, this doesn't satisfy Yankee identities, which is what's so, it's an amazing consistency of Einstein equations. So the divergence of left-hand side vanishes, the divergence of T mu nu vanishes based on energy momentum conservation, but the divergence of this term doesn't necessarily vanish. It's just gradient of trace of energy momentum tensor. It only vanishes for vacuum, but for anything else in the universe, it wouldn't vanish. So that could be an inconsistent equation. So that's why you have to add something to the right-hand side. So here I call that the T prime mu nu. And the equation that this guy should satisfy is that the divergence of this should cancel the divergence of this term. So T prime mu nu's divergence should be 1/4 the gradient of T alpha alpha. And I have to assume something for this T prime because I don't really have enough equations to completely solve for it. And we have played with different things, but here, I'm going to spare you trouble. This is the form that works best basically for this if you assume a perfect fluid for T prime. So it's an incompressible fluid in the sense that its density vanishes exactly, but it has a pressure. So it's a bizarre type of fluid that certain relativists don't like to work with. But you can put it in equations and see whether it fails somewhere or it doesn't. And the unique feature of it is that since it's an incompressible fluid, its speed of sound is infinity, so it doesn't introduce any new degree of freedom into the theory. Even though these p prime and u primes are fields that you have to solve for based on using this equation, there is no dynamics in them. Basically, the same way that sound waves in an incompressible fluid are non-existent. The degrees of freedom of this are also non-existent. Modular a condition about rotation, which is subtlety are going to come back.
What about locality? Sound waves are non-local.
Yeah, so the equations are in a sense non-local, but in fact what it is that the equations are elliptic equations rather than hyperbolic equations. So solving the equations are not going to be numerically very straightforward, but we can do them for incompressible fluids So just the difference is that they're elliptic equations. And you can also show there is no real problem with causality or things like that. But I can tell you more about that if that's something you worry about. Basically, the point is that these are elliptic equations, the fluid equations that you have. And solving them is very similar to solving the fluid equations for a compressible fluid, say, in a river. Okay, so this is the framework. And now the question is, is this already ruled out? So this is an order 1 modification of Einstein gravity. You see, I don't have any free parameter here. The only thing is G prime, which is essentially is proportional to G Newton. So this theory has the same number of free parameters as general relativity. He ought to be ruled out by now. And this is what you think. So this is a Wikipedia page based on PPN parameters. So Clifford will develop this parameterization of deviations from Einstein gravity to next order Newtonian approximation. And then there are now, based on various experiments that are listed here, various ground constraints of order 10 to the minus 5, or even better than that, 10 to the minus 20, and these dimensionless deviations from GR predictions. Now, if you look at it carefully, actually, there is a footnote here. If you go down here, it says, based on the assumption of 6 zeta 4 equals this 3 alpha 3 plus 2 zeta 1 minus the zeta 3. However, there is no direct constraint on the zeta 4. So this is a theoretical assumption which connects 4 of these PPN parameters. But it's just an assumption. And it's valid in some theories, but it doesn't have to be valid in all theories. In fact, if you don't make this assumption, there is essentially no constraint on zeta 4. And it's actually exactly what I was talking, this zeta 4 parameter, exactly what I was telling you about in modifying cosine equation. The coupling to pressure is embarrassingly unconstrained in any test of gravity. Because essentially anywhere that you can see gravity and test it in a confident way, pressure is tiny. So the experiments would be either in the early universe or maybe in the neutron stars, but or in supernova explosions. But those are all, but for the early universe I'm going to come back to, actually for both those situations I'm going to come back to them and tell you what are the concepts.
Is the pressure really negligible in recombination?
Good. So that's the early universe stuff we're going to cover.
You call it early. Oh.
Yeah. I thought it should be early by your standards, isn't it?
No.
It's even by your standards, it's not early. Okay. So I think by most astrophysicists the standard that's early. But no, it's not early universe for string theorists standards, obviously.
But then there's a pretty good test.
But good. So I'm going to show you the constraints on that. And it's interesting that, yeah. So there are already hints that. For this effect, even in the CFE. So this is what we did basically with my good student at PI, who actually came from CITA, I believe, or from University of Toronto. So you can send me any good students like him any day. And so basically what we showed was that this ether theory, first of all, ether actually vanishes in vacuum, which is kind of obvious here. Because this trace of t is 0, t prime satisfies an elliptic equation, and you can show that if ether pressure is 0 at infinity, it's going to remain 0 everywhere. So this t prime is non-existent in vacuum. And in vacuum t is 0, well actually all the right hand side is 0, so the theory is identical to general relativity in vacuum. As long as, with this boundary condition that at infinity T prime has 0 pressure. This P prime vanishes at infinity. So in vacuum, the theory is identical to general relativity. You cannot.
In that theory, the vacuum part disappears, right?
Sorry.
The vacuum part is cancelled, right?
Yes.
So where does vacuum come from?
That's a very good question. Yeah, actually, which I'm not going to answer today, unfortunately. But that's a very good question. Yes, so we have more. So we have some ideas for that. but we don't have a good answer. In principle, you can just add a term to the Einstein equation.
And also, what do you mean that you have to get cosmic equations, because well, you don't have to
Yeah.
it's long enough.
Those are excellent questions, and we may get back to that if there is time. Jumping ahead of myself. So the thing that you can further show is that it's not only in vacuum, but also even if W, the equation of the state of matter, is constant, that P over rho is constant, you can show that the theory is again equivalent to general relativity with an assumption, and this assumption is a bit subtle, if ether and matter move together. And this assumption is a consistent assumption. You can satisfy all the equations, but of course it's not guaranteed. So if you have an initial condition where ether and matter move together, then remain moving together and all the equations are equivalent to that of GR. You can imagine initial conditions where this is not the case and then worry about modifications. And I'm going to touch on that in a little bit. The only deviation from general relativity is this theta 4, which is instead of 0, it's 1/3. So all the PPN parameters we calculated, and they're all 0 except for theta 4. Coupling to pressure, which is 1/3. And the other thing that's more subtle and has to do with this motion of ether and matter is vorticity. So vorticity of matter does not source ether, basically because you only see the trace of measurement momentum tensor. And this would change the intrinsic gravity-magnetic effect by 33%. So you would think that this is already marginally ruled out by either by Lagos or a gravity probe B, and it is true. It's around like 2 sigma. So that's kind of the subtlety of the theory where things aren't quite clear. So if the ether doesn't rotate, but matter does rotate, then there is 33% difference in the gravity-magnetic effect, the Fenn dragging effect that gravity probe B and Lagos measure, and that's at around 2 sigma inconsistent, or you could say, or consistent with their results. Yes.
Please, if you could just remind me, the CITAs are actually responsible for the violation of the conservation of energy and momentum?
Yeah, so that's what people say. And the reason they say that is there is no extra dynamical component. So remember, I'm explicitly conserving energy momentum. But the way I'm doing it is but there is this extra dynamical component P prime here. So I think that what people say about zetas being responsible for violation of energy momentum, that's not exactly true. That's only true in a perturbative setting if you don't have any other dynamical degree of freedom. And here you have this P prime that carries energy and momentum. So I think that's what's happening. That's the statement is a bit naive, or in constrained situation, zetas signify violation of energy momentum. Here I'm explicitly conserving energy momentum because, as I said, this condition enforces energy momentum conservation. So anyway, that's a very good point, and it's a very subtle point, and I'd love to have a better intuitive answer, but I don't. So, what does it do to cosmology? So the point here is, okay, so let me remind you, this W equal to constant is a very, very powerful constraint because actually most places in the universe we have W equal to constant. By most places W is 0 in low relative universe. The only place that W becomes different from 0 or becomes different from constant is matter radiation transition. So that's exactly what Peter mentioned. And the other place would be neutron stars and or supernovae. And we're gonna discuss whether they put any constraints. So in cosmology, matter radiation transition, the prediction of the theory, and you can see this basically in an easy way. Essentially what happens is that the Friedman equation, instead of hs squared being equal to density, is equal to the density plus pressure. So wherever you have rho, you have rho, and you replace it by rho plus phi. And its effect is that basically the G Newton during radiation era and during matter era is different by a factor of 3/4 because pressure is 1/3 of density. So Einstein gravity G during G Newton is the same as G during radiation era. So this factor is 1, but in ether theory this factor is 0.75. So that's 33% or 25% difference. Here I'm listing the constraints on this parameter based on big bang nuclear synthesis, and this is based on CME and large scale structure. So the interesting thing here is that it used to be that helium abundances, so this YP, were inconsistent with this choice, Gn over Gr being 0.75. However, something happened, and I'm not going to discuss the politics of that. All the errors on helium measurements grew. So now both Gr and ether are consistent with helium abundances. The interesting thing is the lithium abundance has been a big issue with BBN predictions. As you can see, it's 3 to 4 sigma up. So this is where the GR prediction is. So this is constraints from CMB. So you should sit here. And lithium is off by a few sigma. However, the ether prediction, you go down here, and you see that you actually, you get much closer. You're almost at the 2 sigma boundary with the lithium prediction, which is this green area. So in fact, you may hope that this ether is actually solving the problem with BBN, which has been long standing for the past 10 to 20 years, as far as I know. And on the other hand, the deuterium, which was bang on from in a standard GR, you are, I guess, after around 2.5 sigma out of the prepared region for deuterium. So it's not quite clear. It seems that the BBN, some data prefers GR, some data prefers ether. But it's interesting because this lithium problem has been with us for a long time and hasn't really had any satisfactory solution. So on the left-hand side, you see the constraints from CME and large scale structure. And you actually see that data is in between the two. Some data actually prefer lower values, and you can actually recognize this as an extra neutrino problem, or extra neutrino, evidence for extra neutrino from CMB, in SPT, ACT, and essentially all cosmological data seem to have some hint for an extra number of neutrinos. However, remember, CMB experiments don't really see neutrinos. What they see is how much radiation gravitates. So you could increase the gravity due to radiation by increasing the amount of radiation, or you could do that by increasing GR, the Newton's constant during the time of radiation. And that's what ether theory does. So here, of course, the answer depends on what data sets you use. If you just use all the CMB data, you get some number that is exactly bang on ether predictions, 0.75. It's at 95% confidence. Here I'm excluding SPT data, so we haven't included that. So this is from a few months ago. Adding BAO pushes the number up. Adding Lyman alpha pushes it down. So the data are somewhere in between the two. And so the jury is out. We probably see these errors shrink as they time come in. And you eventually figure out this is the right answer or this is the right answer for you. So that's the answer to your question. Indeed, CMB has a power, but it's not there yet. It's getting there. Maybe in a year or so. Good. So finally, yes.
So what exactly in CMB is the constraint of it? What do we need to do?
But it's something subtle down in the tail. It's the same as constraining the number of neutrinos. So yeah, it's hard to see it because there are some degeneracies. But I'm just looking at the power spectra. The tails look like around 11,000 or so. They look different. I don't remember which one is higher, which one is lower. But yeah, so it's the same, exactly the same thing as the number of neutrinos.
So you don't need Planck for that in order to do that?
Well, but we do include ACT, but so this is ACT, basically. The blue thing, ACT is ACT plus Stafford. And it's, Yeah, I mean, it's the number I left is 0.75, but the error is big. It is include GR as well. So, so this is the other place you can test this. Is the neutron stars. That's the other place in the universe where we know pressure is big. And again, we know the equations, and the only difference is that wherever we have density, we now have density plus pressure. Of course, you have to include the relativistic corrections as well. And you can calculate the structure of a neutron star and the mass as a function of size. So that's one of the things, the easiest thing you can calculate for a neutron star for a given equation of the state. And you can see that what happens in the ether theory is that the presence of ether effectively softens the equation of the state of neutron stars. So it decreases the maximum mass or the Chandrasekhar mass for neutron stars. And this is the example. So the main problem is that we don't really know what's the nuclear equation of the state. There are lots of possibilities. But there are two different popular equations of the state. I guess my student, Farabot, who did this calculation, compiled it. So it's AP3 and FPS. And the solid lines are a standard equation of the state, the standard general relativity. If you do this with ether theory, you see that the maximum masses decrease. And there are two measurements of a mass of neutron stars that are very high. And in principle, if your theory cannot predict a neutron star as massive as the one that observed, that theory should be ruled out. So if you believe this one, this actually comes out of this university, I believe. René Breton was one of the authors of this paper. If you believe this, that already rules out ether theory. Okay? It's consistent with GR, which is this guy. But the ether theory, none of these equations of the state get as big as 2.4 solar mass. So this measurement is a bit, has uncertainty, so even talking to the authors of that paper, they don't really believe it as far as we know. But this other one is based on a Shapiro delay, has much smaller errors, and is much more reliable. And we are just at the edge of being ruled out. So this AP3, the ether prediction just goes through these two solar mass. So of course, we don't really know what is the right equation of the state. So there is this issue of the right equation of the state. But in principle, this can be tested with gravitational wave detections from neutron star measures, and with order of magnitude estimates show that that might be feasible. So you can actually distinguish between these based on advanced LIGO data. And this is just a visual representation of what happens. So P as a function of epsilon, these are for AP3 and FPS, two popular equations of the states for nuclear matter. And effectively, of course, you're not really modifying equation of a state, but in effect, what happens in ether theory is to decrease these maximum pressures. So that at low energy density and pressure, equation of a state is exactly the same, but at high energy density and pressure, effectively you're decreasing these values. So that's why you're going to decrease the maximum mass. So I'm out of time. So let's try to conclude. So I gave you two lines of argument for two big failures of general relativity. It's problems in the ultraviolet, and it's problems in the infrared, on a small scale and large scale. And at least from a very personal, a very subjective point of view, as to where we're going to see failure of general relativity based on these two sets of issues. So as to the UV problems, most suggestions to UV complete gravity have light fields in them, and I think the most promising place to see the effect of light fields would be the outer galaxy where densities are low. And then the way you can see these effects would be through violation of the equivalence principle. And of course, there will be lots of subtleties, because there could be a violation of the equivalence principle in a standard gravity, as Peter mentioned. But this is an extra effect on top of that, and if you do proper modeling, this can be detected. So the other set of problems with quantum gravity are the infrared problem, and in particular the egregious cosmological constant problem. And so the proposal that I presented to you which didn't include introducing any new parameters, was the gravitational ether. And it discusses the implications for neutron stars, for early universe, or maybe not so early universe, but intermediate redshift universe, and gravitomagnetic effect. And as things stand, maybe this is a bit biased point of view. I think maybe I should say that the cosmological data are mixed between ether and general relativity. Some of them prefer ether. I should put some here. But in time to tell. In the next year or two, somewhere, I don't know if there's anybody in this room who already has the answer. But I guess CITA is a planned institution. So we're going to know in a year or two. And it's going to happen in the CMB. It can happen through data from neutron stars and possibly magnetic effects, or although I cannot be as confident about that. So there are things that I didn't talk about, but some of you asked questions about it. So the actual quantum gravity, what happens in the ultraviolet, there is an idea proposed by Hojava that actually fits very well with this gravitational ether proposal. And that what happens in both these scenarios is that there is an incompressible fluid, basically, which couples to gravity. So in that sense, this is a promising direction from our point of view. There is a question of initial conditions and horizon problem, and Shinji Mukayama has broken this, so maybe you don't need inflation to solve initial conditions. This scenario, in the context of actually Hojava gravity, might have a solution. Joao Maguejo has broken this from different directions, but they both rely on this incompressible fluid. How you can explain dark energy? So this is more speculative, but we have a proposal based on connecting basically black holes to this theory, and so it seems to give order of magnitude correct result, but the details are basically too hard to work out for us. So we're not really sure whether the details work, but we get the right order of magnitude for the effects of dark energy. And there are lots of open questions. Is there an action? How would a structure formation work in this scenario, especially if we include dark energy? And then the other big question, that's the question that Muhammad has worked on, is if you have this violation of Lorentz invariance, or in a sense, if you have this fluid present around us, how come the physics is in infrared where we see things are Lorentz invariance? So the emergence of Lorentz invariance, from my point of view, is really the biggest problem in this context. And okay, so this is a self-cosmological thing. So there's cosmologist quantum gravity solutions. And I guess I just have a quote from Einstein. More careful reflection teaches us, however, that the special theory of relativity does not compel us to deny ether. So there you go. Thank you. From WMAP or? Yeah, I mean we include all the data sets that are out there. I don't think it makes much of a difference because I think most of the constraints come from high LCMB where there is no polarization. I mean it's the same constraints on the number of neutrinos, and I think they come from ACT and SPT, which has no polarization.
So it's mainly the pictures.
Well, probably because we don't have very good polarization. But I don't know whether there is anything specific that you can see in polarization, but not in temperature. Yes.
In the modified gravity theory, how are black holes modified?
How black holes are modified? So that's a great question. So that's kind of, as I said, the vacuum theory is identical to general relativity if the right hand side vanishes, assuming that pressure of ether vanishes at infinity. And that's the thing that can be modified in cosmology, because we know that in cosmology you don't really have an asymptotically flat space-time. So in fact there is an extra, because I don't have it here, there is an extra integration constant that you solve for Schwarzschild methods. to do with the pressure of ether at infinity. So there is this extra thing, and the idea, which was very suggestive at the time, was that maybe this pressure of ether at infinity would be the dark energy pressure. So there is this an extra integration constant. So that's basically how the structure of black holes are modified. So then what we did was to come up with a proposal of basically relating the mass of the black hole to the pressure of ether at infinity. And it turns out there is a natural way of doing it. And so the interesting thing that we got excited about was that the pressure happens to be m Planck times Hawking temperature cubed, which happens to be the same as dark energy pressure for stellar black holes. So somehow this mass combination that comes out of our calculation is the same as dark energy pressure for most of the black holes in our universe. So that's the interesting coincidence. But in the details, it wasn't really easy to fit in the details. But for a single black hole, that's what happened. There's an extra integration constant. And that integration constant, in a sense, actually becomes important very close to the horizon and at infinity. That's what's the thing that's interesting about, very unique about this theory. There was this integration constant that, in addition to the mass, that controlled physics very close to the horizon of black holes and at infinity.
How about the relation with electromagnetic field?
Yeah, so trace electromagnetic field is zero, so it doesn't make any difference. Yes.
Isn't this integration constant reintroducing the cosmological constant? So now your question is, okay, why is integration constant exactly?
No, it's an interesting question. At the static level it is, but the difference is that this is a constant in the space, not a constant in time. And if you have a compact space, for example, you don't have this integration constant. So like you can solve Friedman equation. For a homogeneous universe, you don't have an integration constant. So that you can do predictions, that's what we did. So there is absolutely no constant there. So if you introduce black holes, that gives you an extra boundary, basically. And that's where things become ambiguous, so you get this extra integration constant. So the presence of the spatial boundaries gives you this extra constant. And then, yes, in some sense it is similar, but it only comes in when you add black holes, basically. So that's the thing.
Okay, I think we're running a little over on time, so let's move the discussion up to the cookies upstairs. Thank you, Niayesh, again.